So, as most of you here, I'm interested in making machines see the world the way we see it. And when I say machines, I'm thinking of autonomous cars or robots or systems for augmented reality. These are all very different applications, of course, but in many cases, they have one thing in common. That is that they require low latency processing of the visual input. And in our work, we use deep artificial neural networks, which, as you know, maybe, consist of a series of layers. And we feed in an image, and then this image is processed by each layer of the network, and then we obtain a prediction, assuming that this is an object detector, and there's a cat there. We care about cats a lot. So just to make it clear what I mean by latency, that is the time that passes between the moment when we feed in the image and the moment when we get the prediction. And here, obviously, the latency is just the sum of the computational times of all the layers in the network. Now, it is common practice that if we are not quite happy with the accuracy of the system, we can make the systems deeper by adding more layers, because this increases the capacity of the network, the expressivity of the network, so we get better accuracy. But this doesn't come for free, of course. This will lead to increasing the processing time, the latency of the system. So to the point where current object detectors run at around 5 frames per second, which is great, of course. But what does 5 frames per second mean in real world? And I hope you can see the difference between the two videos here. So on the left, you see the normal video at 25 frames per second, and on the right, you see the 5 frames per second video obtained by keeping every 5th frame in the video. And I can tell you on the right, the tennis ball appears in 2 frames. So if your detector is not perfect, it might fail to detect it. So then you're left playing to play tennis without seeing the ball, which is probably not ideal. So then the question is, how can we do autonomous driving at 5 frames per second, for example? And one answer could be like this, turtle power. We all move at turtle speed, but probably that's not what we are after. So then we need to get some speed from somewhere. One option, of course, is to rely on hardware. Hardware has been getting faster and faster in the past decades. However, faster hardware normally comes with higher energy consumption. And we know that on embedded devices, this is a critical constraint. So then, what would be more sustainable alternatives to get our models faster? So let's look at what the brain does to process the visual input. There are lots of numbers there. Don't worry, I'll walk you through. So this, I'm just giving a loose comparison between a generic artificial neural network and the human brain. So let's start by looking at the number of basic units, which in the brain, you know, are called neurons, and their connections are called synapses. Here, the brain is clearly superior to any model that we have so far by several orders of magnitude. And this could explain, for example, the fact that the brain is able to process so many things in parallel and to achieve such high accuracy. However, when we look at speed of basic operation, here we can see that actually our electronic devices are much faster than the brain. And the same goes for precision of computation. Here, again, the electronic devices are much more precise. However, as I said, speed and precision of computation normally come with high power consumption, to the point where like, a current GPU will consume about 10 times more than the entire human brain. So, and yet, with all these advantages on the side of the electronic devices, we are still running at 5 frames per second when the human brain can actually process more than 100 frames per second. So this kind of points to the fact that we are doing something clearly suboptimal with our artificial neural networks. And I'm going to argue here that the reason for this suboptimal behavior comes from the fact that current systems consider the video as a collection of independent frames. And actually, this is no wonder, since the current video systems were initially designed as image models, and then we just run them repeatedly on the frames of a video. So by running them in this way, it means that the processing is completely sequential, well, except the processing that happens on GPU, where we can parallelize things. But overall, it still remains sequential. Then all the layers in the network, they all work at the same pace. And this is kind of opposite to what the brain does. So there is high evidence that the brain actually exhibits a massively parallel processing mode, and also that the neurons fire at different rates. And all this because the brain rightfully considers the visual stream as a continuous stream that exhibits high correlations and redundancy across time. So just to go back to the initial sketch, this is how our current systems work. So you get an image. This goes through every layer in the network. You get a prediction. Next image comes in. It goes again through every layer, and so on. What you should observe is that at any point in time, only one of these layers are working, and all the others are just waiting around for their turn to come. And this is clearly not useful. It's just wasting resources. And the other thing is that everybody works at the same pace. And again, this is not needed if we take, for example, into account the slowness principle. And I'm just trying to depict here what that means. This principle informally states that fast varying observations are explained by slow varying factors. So if you look at the top of the figure on the left, those are the frames of a video depicting a monkey. So if you look at the pixel values in the pixel space, you will see high variations because of some light changes, or camera moves a bit, or maybe the monkey moves a bit. However, if we look at more abstract features of the scene, for example, the identity of the object or the position of the object, these will change much more slowly. Now, how is this relevant for artificial neural networks? It is quite well understood now that deeper layers in an artificial neural network extract more and more abstract features. So if we agree with this slowness principle, then it means that the deeper layers can work at a slower pace than the layers that are at the input of the network. So now, if we put all these observations together, we obtain something like this. We obtain like a Christmas tree, if you want, where all the layers work all the time, but they work at different rates. So we are pipelining operations, and this generates more parallel processing, and we can now update our layers at different rates. Now, the important result of all this is that now so initially I said that the latency of a network is given by the sum of the computational times of all the layers in the network. Now, very importantly, with our design, the latency is now given by the slowest of the layers in the network. So in practice, we obtain up to 4 times faster response. I know it's not the 10 times, but 4 is actually enough, because once you're in perception, once you're past 16 frames per second, then you're quite fine, actually. And we obtain this faster response with 50% less computation. So I think this is not negligible. And again, very important, we can now make our networks even deeper to improve their accuracy without affecting the latency of the network. So I hope I've convinced you that this is a more sustainable way of creating low latency video models. And I'm looking forward to the day where our models will be able to process everything that the camera can provide. And I'm just showing here a beautiful video captured at 1,000 frames per second. So I think this is the future. Thank you.